thank you. Thanks for the invitation. So I'm going to be a tablet talk. So I'm just going to get my screen sharing started.
Not yet.
Should be going now.
Yes.
And then it's good. Okay, so I'm going to talk about hidden invariance of last passage percolation and directed polymers. So I'll just start by introducing the models. So I'm going to start with an environment M, which is just a collection of random variables on Z2. So these are always going to be, basically for the purposes of the talk, IID random variables. And then I'm going to use the notation U for a box in Z2. So the picture is like this. So if I draw some portion of Z2, then, okay, U is going to be a box. So something like this. So I can specify the box by its opposite diagonal corners. So I can look at the southwest and northeast corners. I'm going to call these U minus and U plus. Okay. And then I'll start by defining the last passage value in this environment M across the box U. So this is just Zm of U. And it's going to be the maximum over all paths pi, which I'll specify in a second, of the sum of the vertices in pi of the weight at that vertex. So here, this maximum is over upright paths pi going from U minus to U plus. So I can sort of add a sample path to this picture. It would look maybe something like this. So this is 1 pi, and you just add up all of the weights along this path. Okay, so Zm of U is this is the last passage value across the box U. Okay, and for later in the talk, I'll also use multi-path last passage values. So now if we have a vector U, so this is going to be U1 up to UK. So this is a collection of, this is a vector of boxes. I can define Zm of this vector U. This is now basically defined similarly. So it's the maximum over paths pi 1 up to pi k of the sum I equals 1 to k, sum over v in pi I, mv. And again, these paths pi I go from, the paths pi I go from ui minus to ui plus. And the important distinction with these multi-path last passage values is that we specify that our pi I are always disjoint. So the picture here is, okay, I have a bunch of starting points. I have a bunch of ending points. I'll just draw it with 2. And I'm taking the maximum weight over all disjoint paths between these points. Okay, so this is last passage values and multi-path last passage values. Okay, and then the other part of the talk is about directed polymers. And again, the context is going to be directed polymers on Z2. So I'm going to define the directed polymer partition function in almost exactly the same way. So again, we can have this environment, and we define the directed polymer partition function as Zm of U is the, instead of the maximum over pi, we look at the sum over all paths pi with the product of the weights replacing the sum of the weights. Okay, so it's essentially, the definitions are exactly the same as in last passage percolation, except we exchange max and plus for plus and times. And the reason I'm using the same notation for both of these is for the purposes of this talk, really there's no need to distinguish between these models. So that, I mean, there are many differences, but just for what I'm going to be talking about today, we can treat them in the exact same way. And again, you can also define multi-path partition functions. The one thing I will mention with the difference between the models is for defining last passage values, it makes sense to let the random variables take any values or any real values. When we're defining polymer partition functions, it's going to make sense to let these random variables be always between 0 and infinity. So the idea is that we want, okay, this is essentially a partition function, so it should define a probability measure on paths, or it should be the normalizing constant for a probability measure on paths. So we want Zm of u to always be positive, and for that reason, we want these weights always to be positive. So it's kind of a minor distinction which won't really come up. Okay, so that's the definition of the models, and then what I'm going to be talking about today is sort of interesting symmetries of these models in particular integrable cases. So the reason I got interested in this was there was a recent work of Gorin, and Wheeler. And they found sort of a surprising hidden invariance, or hidden shift in variance structure for another integral model called the colored stochastic 6-vertex model. So they found a shift in variance for the colored stochastic 6-vertex model. Okay, so the details of that model aren't so important for what I'll be talking about today, but if you aren't familiar with it, we'll just say that it's quite related. And in particular, certain degenerations of the colored stochastic 6-vertex model give you directed polymer models and last passage models. Not the models that I specifically stated above, but I'll sort of get into that more in a bit. So let me say what their shift in variance statement would say in the context of these models. So in the context of Z2 LPP and directed polymer models, this invariance says, okay, so we have, I'm going to give this invariance in pretty much the simplest case. They prove more complicated things as well, but let's start with something quite simple. So I'll have a big box U and a box V, which crosses U in the sense that every path between the two corners of V crosses every path between the two corners of U. So these paths just need to intersect. These two endpoints could coincide. And then let me draw another box W, which is just going to be V shifted horizontally. So again, W and U have the same crossing structure where every path from the two corners of W crosses every path from the two corners of U. And so this shift in variance for the stochastic 6-vertex model, if you think about what it should say for last passage and directed polymers, it gives you that Zm of U, Zm of V is equal in distribution to Zm of U, Zm of W. Okay, So it's really, first of all, I should say this, in our case, this doesn't hold for general M. So certainly it's a surprising thing that this should hold at all, and it really is something special about the integrable structure of these models. So, but I'll say, but based on their work, it's reasonable to expect shift invariance for certain integrable choices of the environment. Okay, so so I went to this, I went and I heard Vadim talk about this. And I found this really interesting, but I would say that the talk, and he raised these questions in the talk, it sort of raises a lot of different questions. So the first thing is, of course, what about other models? I'm sort of mentioning this in the context of last passage and directed polymer models. So can you get shift invariance for other integrable models? So their proof applies to the colored stochastic six vertex model, and there are many integrable degenerations of this model. So like the colored TASEP, the beta polymer, Brownian last passage percolation, but there are many other models where you might expect this to hold, but their proof is very specific to the colored stochastic six vertex model and doesn't easily adapt. So you can ask, what about other models? A second thing is, what about other invariances? So this is a nice shift invariance, and they proved stronger statements than this, but they also had a conjecture about a stronger type of shift invariance. And you could ask, well, is that all there is, or are there sort of many more interesting shift invariances? And their proof, while it gives you this one, it seems to, they did have this conjecture, and the proof sort of falls short of being able to prove that. Stronger shift invariance, which I'll get to later. And the third thing is is the question of, is there a simple proof? So their proof is, I would say, it's quite involved. It's very nice, but it relies on a delicate induction argument, Lagrange interpolation. You're using the full inhomogeneity in the colored stochastic six vertex model. And so it seems natural to ask, well, even if you choose a simpler model, maybe you can have a simpler proof. And in fact, there is one degeneration where they can find a simpler proof, but this is there's one degeneration of the colored stochastic six vertex model where their proof reduces to a statement about local times of simple random walks. But this is sort of so far down the hierarchy that this statement was already known. Okay, so the goal of today is basically to address these questions for last passage percolation / directed polymers on Z2. And the way I'm going to do this is via properties of the Rsk bijection, or in the case of directed polymers, the geometric Rsk correspondence. So these, and I'm going to say that the methods today, I think they can be adapted to any situation where you sort of have a really nice version of the Rsk or geometric Rsk correspondence, which is basically which I would say is limited basically to the models that I'm going to talk about here. So regrettably, this proof doesn't work for the colored stochastic six vertex model itself, where you don't have a version of Rsk. And the other thing I should say is, so I posted this paper in January, and recently after I posted this, sort of shortly after I posted this, a paper came out of Pavel Galashin, which proves some stronger invariances and gives a nicer proof of the Borde-Ingor-and-Wheeler result in the context of the color stochastic six-vertex model, based on sort of a new and unexplored connection with Hecke algebras. So this is this extends Borde-Ingor-and-Wheeler for the colored stochastic six-vertex model and its degenerations. But again, that proof is specific to the colored stochastic six-vertex model. So for example, it isn't going to apply to lattice last passage percolation. And it would be interesting to see if my proof and any of the colored stochastic six-vertex model proofs can be somehow applied to the other model. All right. So I'm kind of going to start from the basics with the role that Rsk plays in last passage percolation and the role geometric Rsk plays in directed polymers. We're only going to use a few simple consequences for what we're going to talk about today. So what is Rsk for us? So again, U is going to be a box in Z2. I'm going to define a particular vector UK, which is going to be U minus U plus K minus 1, 0. So this is going to be a particular K tuple, which is sort of a bit clearer when I draw it, what this is. So if I have this box U, then UK is a vector of boxes, and the first one looks like this should be a minus sign. And the first one looks like this, and then you sort of shift over by 1 each time until you get to the end. So in particular, what multipath last passage looks like for UK. So if I look at Zm of UK, I'm going to be optimizing over paths that look like this. Okay. And I'll let D of U, this is just going to be the set U, U2, U3, and so on. So Zm on the set D of U, you can think of this as all, maybe, this is going to be all multipath last passage values that cross, maybe that go between the corners of U. I should say that when, if I choose K too large, then Zm of U to the K is not defined. So, in the definition of D of U, we sort of truncate this at the last value of K for which we can actually define this last passage value, because if it's too large, then there no longer exists disjoint paths. And the reason you really should think of this as going diagonally between the corners of U. I know there's sort of a horizontal shift set up in the definition of UK, but in order for this disjointness condition to hold, what needs to happen is this first path has to go up vertically for a while, and then the second path needs to go up vertically for one less, and so on. And then similarly on the other end. So really with these last passage values, you have some fixed weights that you're picking up in the corners, and then you're just going diagonally between those two regions. Okay. So now we're almost ready to define Rsk. So I'm going to define Rsk from my point of view on an n by m box. Okay. So I'll define two more sets of endpoints. I'm going to say that H of 1n cross 1n, this is the union from I equals 1 to n, or from I equals 1 to m rather, of d1n cross 1i. So these are all these diagonal multipaths that go like this. So we start with d1n cross 1, 1, and we sort of keep moving up. So Zm restricted to H of 1n cross 1m, this is going to be recording all multipath last passage values starting at this corner and ending at some point on this side. So the H is because these are kind of crossing the box horizontally. Okay. And then similarly, V is going to be all multipaths that cross the box going vertically. So this is union I equals 1 to n of d1i cross 1n. And what the Rsk correspondence is this is basically a map from M to, say, M on a box U to Zm restricted to H of U, Zm restricted to V of U. So in the usual presentation of Rsk, these two are your two semi-standard Young tableau. They contain the same data as the semi-standard Young tableau. There's a fairly straightforward way to go between them. And combinatorially, the thing you learn about Rsk is that it's a bijection. But the only thing we're going to use probabilistically is that if you pick, if you have a bijection, if you pick M in the correct way, you should get some interesting probabilistic structure. So the probabilistic upshot here is that if you pick M to be IID geometric or exponential, then Zm restricted to H of U and Zm restricted to D of U, these are conditionally independent given the shared information this one should be a V, sorry about that. And Zm restricted to V of U are conditionally independent given Zm restricted to D of U. So the multipath last passage values in a geometric or exponential environment from the corner to the top and from the corner to the right side are conditionally independent given all of these diagonal last passage values. So that's Rsk. The story for geometric Rsk for us is exactly the same. So for geometric Rsk, you have the same independence statement. For directed polymers, when M is an inverse gamma IID environment. So this is the log gamma polymer. Okay, so really and again, as I said, we're going to treat these structures exactly the same way. The important thing here is that you have this conditional independence statement. Okay, so this is the kind of, Rsk gives you this partial decoupling structure for certain models. And what's maybe less known about Rsk is that these two sets of, say, last passage values, Zm restricted to H of U and Zm restricted to V of U, contain some more information than you initially see. So this is, I'll state this loosely as a theorem. So Zm restricted to H of U, this actually contains, I'll state it loosely to start. So this contains all last passage values going from left to right across U. So let me state this a bit more explicitly. So this Zm restricted to H of U, this is all your multi-path last passage values starting at this bottom corner. But if you change your starting point, the last passage value, say from here to here, is also contained in Zm restricted to H of U. So a bit more formally, I can write maybe H bar of U, which is going to be the set of boxes V contained in U, where V and U have the same columns. So the point is that Zm on the set H bar of U is actually some function of Zm on the set H of U. So there's some explicit measurable function, or there's some explicit, there's some explicit function f, which takes the last passage values from the corner and gives you all last passage values from one side to the other. And of course, the same is true in the vertical setup. So Zm restricted to so all last passage values from bottom to top are contained in all last passage values from the bottom corner to the top. And so this is true for Rsk with last passage values. It's also true for geometric Rsk with last passage values replaced by partition functions. Okay, so this theorem, you can actually deduce this from properties of the Schutzenberger involution. I kind of became aware of it because in a paper that I wrote a couple of years ago, some of my co-authors had realized that this was true with an explicit form for this function f. And later we found that that same result had been discovered sort of much earlier by, I'm going to say, in a paper of Bian, Bougerol, and O'Connell, though I wouldn't be surprised if, in a paper of Bian, Bougerol, and O'Connell, there's also another paper of Nomi and Yamada from around the same time. And both of them kind of, they might not state this theorem in this exact way. They especially, they might not say this theorem in this exact way, but really they contain all the essential ingredients, just sort of pick this theorem out of their papers. Okay, and I thought about giving a proof of this, but so if there's interest, I can give a proof of this maybe after the talk, which is based on distilling these methods of Nomi and Yamada.
So Duncan, I have a question, if you don't mind. Your theorem is stated in this language of last passage times, but the usual Rsk gives is given by in the language of Tableau, for example. Does there exist a statement of this exact theorem in the language of Tableau?
So you can, I mean, you could, the statement of this theorem. So you basically so if you look at the usual Rsk bijection where then this Zm restricted to H of U and Zm restricted to V of U, these are just the two tableaux that are the output of the Rsk bijection. And usually you would talk about these last passage values as being lengths of long increasing subsequences, something like this. So what this theorem would say is that if you, basically what this theorem would say, let me kind of put this in a little bit more RSK form, is that if I look at my matrix in RSK and I want to know the length of the largest weight path from, say, this point to this point, then this is contained in the corresponding tableau in a, I always get these two confused, but there's one of the tableau is going to contain all of the longest weights of paths from the bottom to the top, and the other tableau is going to contain all the largest weights of paths from the left to the right. Does that clear it up?
Yes, thank you.
Okay. Okay, so basically we can use this theorem. Maybe I will combine, I'm going to combine this theorem with the previous statement about RSK to say the important consequences that Zm restricted to H of U bar and Zm restricted to V of U bar. So left to right and bottom to top last passage values are conditionally independent given all of these diagonal last passage values. Again, this is when M is geometric / exponential, or inverse gamma when we're working in the directed polymer case. So this is a really rich decoupling structure, and we can use this to pretty quickly get some interesting shift invariance statements. So let me, I'm going to use this to prove basically this picture that I drew up here. So I'll redraw it downstairs. So let's just draw this again. So I'll have U. W and V in red. And the theorem we can now show is that Zm of U, Zm of V is equal in distribution to Zm of U, Zm of W. Okay. So first, I'm going to let Z be the box containing W and V. So the way I've set it up, we can just write Z is W union V. I'll draw that in the picture. Okay. So Rsk is getting too messy. This is my Z. So then if I look at Zm of U, I can see that Zm of U only depends on the last passage values for W and Z, say, or for W and V, say, by what's happening in the box Z. And in particular, because I'm going to be optimizing over paths that look like this, they always go from the left to the right across Z. So for example, what I could say is that, maybe let me write out this full expression and then explain what I'm doing here. So then I'll write Zm restricted to D of U, Zm of B. So what I've written here is actually I guess a 3-step Markov chain. So the point is that because Zm of H bar of U and Zm of V bar of U are conditionally independent given Zm of D of U, you can see that, okay, Zm of v is something that's going from the bottom to the top across this box Z. Zm of h bar of u and Zm of u only require information that's going from the left to the right across Z. Okay. So what I've done is I've decoupled Zm of u from Zm of v. So this is a 3-step Markov chain by this conditional independent structure here. And I can similarly create a Markov chain involving w. So Zm of u, Zm h bar of u, Zm d of u, and Zm of w is also a Markov chain, okay? Just by this conditional independent structure. So if I want to check that Zm of u, Zm,
Could you explain, I'm having trouble following what each one of these means. Could you just explain in the context of the picture what each of these things?
Yeah, of course. So Zm of u and Zm of v, hopefully those are just last passage values. Maybe I can, I'll draw v here. Zm of h bar of u, this is everything going from the left to the right. I think one reason you might be confused is because I'm getting my notation confused. So this should be a Z, should be a Z, should be a Z, this should be a Z. Okay, so Zm of h bar of Z, this is everything going from the left to the right across Z. So we can see that if we're trying to think, okay, how does Zm of u depend on this box Z? Well, all it takes in is last passage values from the left to the right. And then there's some independent information over here and some independent information over here. Okay. So now Zm of d of Z, this is, so we know last passage values from the left to the right, these are conditionally independent of last passage values from the bottom to the top, given last passage values that go diagonally across. So that's this Zm restricted to d of Z. So that's what allows us to do this decoupling. Does that make sense?
So first of all, the Zm h bar of z, I guess that can include things that are beneath the u box as well, right?
Yeah, it includes things that are beneath the u box. So this is just everything going from the left to the right across Z.
And so so you're saying it's the transition from the Zmu to the Zm h bar z is Markovian. Is that clear? Or
yeah, okay. So, I mean, basically what you do, in order to check that each of these are Markov chains, you'd need to check that, okay, I can go through this a bit more slowly, say that if we fix either this entry or this entry, then what comes before and what comes after, these are conditionally independent. Okay, so if we fix Zm of h bar of Z, then Zm of u is determined entirely by Zm of h bar of Z plus some entirely independent information. So in particular, it's going to be conditionally independent of Zm restricted to d of Z and Zm restricted to v. Okay. On the other hand, Zm of h bar of Z and Zm of v are conditionally independent given Zm restricted to d of Z by this decoupling property of the model. Does that make sense?
Mm-hmm.
Okay, it's good to spend time on this because this is really I don't know, I would say this is like the main idea, is just turning this decoupling information into short little Markov chains. All right, so back to the proof, back to the end of the proof, we have two 4-step Markov chains. If we want to check that Zm of u, Zm of v is equal in distribution to Zm of u, Zm of w, we just can check that these Markov chains have the same distribution. And for that, we just need to check that they have the same transition probabilities, or in other words, that adjacent pairs always have the same distribution. So Zm of u, Zm of h bar of Z, this is the same thing as this first pair here. Again, we have the same thing as the second pair here. So the only interesting thing we need to check is that Zm restricted to d of Z, Zm of v, has the same distribution as Zm restricted to d of Z, Zm of w. So let me redraw this. to make it a bit clearer. So this will be my Z. I'll draw it twice. Zm restricted to D of Z, this is basically things that go diagonally across Z. And I can draw in V and W. So V looks like this. And W looks like this. So I care about that value. And I care about this value. And what you can see is to go from one picture to the next picture, I just perform a 180-degree rotation. Okay, and because my environment was IID, last passage values are invariant under this 180-degree rotation. So these two are equal in distribution by a simple rotation invariance. Are there any questions about this, the basic proof strategy? Okay, so what I was going to say, I have some pre-drawn pictures below. I'm going to try and maybe I'll skip past those. And just say, okay, so we proved a simple shift invariance, but this principle of creating Markov chains and using this decoupling, you can use it to get all sorts of shift invariances and other interesting invariant statements. So we can have this strategy. Maybe actually, let me start this well below just in case I. So we have a strategy for finding invariance. So basically, if we want to show that xy is equal in distribution to zw, where you should think of these as sets of last passage values or sets of partition functions, what we need are Markov chains x, x1 up to xk, y, and say z, z1 up to zk, w, with equal transition probabilities. Okay, and we can check that these are Markov chains by the Rsk decoupling structure. So this decoupling structure coming from Rsk or geometric Rsk, that's going to help show that they're Markov chains. And how are we going to check that they have equal transition probabilities? Well, we can use sort of really basic invariances. So by using rotation, reflection, and translation invariance. Or, you know, once you've established some things, you can build up and use previously established invariances as well. Okay. And you can really start exploring this and see, okay, what sort of statements can you get? So I've drawn a couple of examples here. So this first one was actually, this first thing was conjectured in the Borden, Gorin, and Wheeler paper. So let me explain what's happening in the picture. So I've drawn three big boxes in, say, the first part of this picture. And I'm going to think of this capital U as all boxes whose southwest corner is over here and whose southeast corner is over here and whose northwest corner, and southwest corner is over here and whose northeast corner is somewhere in here. So U is a collection of boxes. Capital V is all boxes that start here and end somewhere up top there. And W is all boxes that end up here and start somewhere down here. So Okay. And then what I could do is I'm going to keep all my boxes in capital U fixed, and I'm just going to shift the boxes in V. So they shift like this to get F of V, and the boxes in W, I can also shift these. So they've sort of been shifted as well to get G of W. And what you can show is that the joint distribution of Zm on U, Zm on V, and Zm on W is the same as Zm on U, Zm on the shifted version of V, and Zm on the shifted version of W. Okay, and it's sort of by almost just iterated application of this proof method and building up more complicated statements. Okay.
Can you explain the shift again? Like, how are you shifting it?
The shift, so F, you should think of this function F as just translating all of the boxes, all of these boxes. So yeah, maybe I can draw this with, it's kind of hard to draw. So say I had two boxes here, then my shift F would just be translating them in some way, all with the same translation. Does that help? Does that make sense?
Yeah, thanks.
So one of the important things that's happening here is you'll notice that, so one path from a box in W is drawn, but you'll notice that any, say, path for a box in U crosses that path, and the same is true over here. So if we draw a path in U, it always crosses this path crosses the shifted path as well. So it's always important that we maintain this crossing structure. Otherwise, you won't keep invariance. But you could also ask, okay, can you get interesting invariance statements when you don't have a crossing structure? And so one way you could do that would be if you have a disjointness structure as well as a crossing structure. So that's the second example. So here I've just drawn 5 boxes. So I have U1, U2, U3, and V1 and V2. U1, U2, and U3 are all disjoint from each other, and V1 and V2 cross the V boxes always cross the U boxes. So basically any permutation and sliding around of these boxes will preserve the joint distribution of last passage values as long as you maintain the disjointness of the V's, the disjointness of the U's, and the crossing structure. So here, for example, I'm permuting the order of these 3 boxes, U3, U2, and U1. So U3 goes to U3 tilde, U1 is going to U1 tilde there, and U2 is going to U2 tilde over here. And I've also permuted the V's. But the important thing is the disjointness is kept, and the fact that the V's always cross the U boxes, that's kept as well. And so the statement you get is that the joint distribution Zm of U1 up to Zm of U3, Zm V1, Zm V2 is the same as the joint distribution when I shift these boxes around and possibly permute them. So those are 2 examples. I'm going to give one more example. So here I have 2 boxes U1 and U2 and 2 boxes V1 and V2. And the V boxes always cross the U boxes. So you can see you have this crossing structure. So there's a crossing structure here as well. But the U boxes are no longer disjoint from each other, and the V boxes are no longer disjoint from each other. So you can think of this as sort of, and so when you have this sort of interaction, which is not, the boxes aren't crossing each other and they're not disjoint, if you want to preserve the joint distribution, you need to preserve the way that these 2 boxes connect to each other. So in particular, the kind of shifts that I can do are going to keep the U boxes in place and keep the V boxes in place and move them in some way like this. So that's what's happening here. is if I take my U boxes and I sort of shift them down so that the interactions between the U's and the V's remain the same, and the U's always cross the V's, then I again have a new type of invariance here. And you can try and come up with lots of interesting interlocking puzzle piece invariance statements if you want to. Okay, the other thing I wanted to say is that you might think from these examples, one reasonable guess would be, okay, if I just make sure that my boxes always, basically, okay, maybe let me start this sentence again. So one thing you might think is, it seems like the important interaction is just pairwise interaction here for preserving joint distribution. So we either need to make sure that we preserve the particular angle of intersection, or the particular way in which two boxes intersect but don't cross. We need to preserve the fact that they cross, or we need to preserve the fact that they're disjoint. So it turns out that that's not enough to give you invariance. So I gave here's a quick non-example of that. So here I have three boxes, U, W, and V. So here V is just a single square in Z2. And W is just a strip. And U is a box which contains them both. So W crosses U. And so if I got rid of this box V, then the joint distribution of Zm on U and Zm on W is the same as the joint distribution of Zm on U and Zm on W tilde. And the same is true if I look at Zm on V and Zm on W, and Zm on V and Zm on W tilde, because W tilde and V and W are all disjoint. But if I look at this triple, Zm on U, Zm on V, Zm on W is actually not equal in distribution to Zm on U, Zm on V, Zm on W tilde for any of these, for any model of last passage percolation or directed polymers, for any of the three integrable examples. Okay, so hopefully this kind of gives a flavor for the kind of things you can prove. I'll just mention a few more things about this. So we have kind of three basic models here: geometric and exponential last passage percolation and the log gamma polymer. These have various degenerations. So all of these invariance statements also pass over to the degenerations. So maybe your favorite one might be the KPZ equation. Gets new invariant statements, as does the Airy sheet. Brownian last passage percolation, there are others as well. Okay. The other thing you can do is there's sort of a rich enough set of invariant statements here that you can ask about invariant statements of other objects other than just, say, last passage times and partition functions. So I'll give one example, which is just about last passage geodesics. So pi is a geodesic if Zm of U equals the sum over V and pi of MV. So it's just a path that optimizes this, or a path that achieves this maximum in the definition of last passage percolation. So I have three boxes here, W, U, and V, and I've drawn sample geodesics here. So the geodesic, if you choose exponential last passage percolation, which we'll do to make this simple, these geodesics are always going to be unique. So there's a unique optimizing path for exponential last passage percolation. And what you can conclude is basically if you forget about this region in the center where everything is overlapping, then the joint distribution of the part of the geodesic for W and the part of the geodesic for U is the same as the joint distribution of the part of the geodesic for W and the part of the geodesic for V that don't lie in this intersection. So I'll write that down precisely. So it's pi of W, pi of U, pi of V, these are the geodesics. Then if I look at the part of W, the part of pi of W that doesn't hit the two boxes U and V, and I look at the part of, say, pi of U that doesn't hit the box W, then this is equal in distribution to the part of pi of W that doesn't hit U and V, and the part of pi of V that doesn't hit W. So the one thing I should say when I write this joint distribution is I need to be a bit careful because pi of U and pi of V don't start at the same exact place. They're starting at different points in the plane. So I would need to make this sort of statement technically correct, I need to introduce a shift. So maybe I'll let T going from V back to U be the shift, which just sends pi of V back to, which matches up pi of V with pi of U. So you can do this sort of thing. You can prove shift invariance statements for geodesics. The analog in the polymer context is you can prove shift invariance statements for the quenched polymer measure. You can analyze things like disjointness probabilities, branch points. You can do last passage and directed polymers with initial conditions. So sort of any statistic you can think about, there's probably some shift invariance statement which you can come up with about it. Okay, and yeah.
There's a question by Leonid.
Mm-hmm.
What is the applicability of the Markov chain method, percolation and polymers, but not vertex models?
I think, yeah, I think you need a pretty, I think it doesn't work unless you have an analog of RSK or geometric RSK, basically. So I mean, I don't know in terms of, I haven't thought about what you can do in the context of vertex models, but certainly like I mean, it doesn't work for the stochastic 6-vertex model where you don't have a nice analog of RSK. Does that answer the question? But yeah. my hope would be it can extend, and my hope would be, you know, it's just once analogs of RSK and geometric RSK are found for those models, then you can sort of apply this method. If you know,
there are analogs and analogs. It doesn't. There are no bijections, but
yeah. So the question is kind of how good, like if the analog is providing the right information. Like if you have an analog which is providing this sort of decoupling information, and also this theorem about last passage values from, say, the bottom to the top being contained in last passage values from one corner to the side. This I've only proven for RSK and geometric RSK. I don't know for these, yeah, for these more exotic analogs which aren't bijections, which are probabilistic. I'm not sure. Okay, maybe the last thing I'll mention, I know that the talk doesn't really have a time limit, but I don't want to go too far beyond an hour, is you can use this method to get new versions of RSK So what I mean by this is, for those who are familiar, for those who are familiar with RSK, you've probably seen RSK bijections on, say, the square, and there's also RSK on Young diagram-like shapes. So you can also get, using this method, you can recover RSK bijections for shapes that look something like this. Say. So the general type of shape is a Moon polyomino. So I won't get into that too much, but you can have a version of RSK for these shapes with this method. And you can also get different versions of RSK for boxes, where instead of looking at the diagonal last passage values as you go sort of across like this and up like this, you can start somewhere in the middle and extend left and right as you choose. And then you can also do the same on the other side. So you can start in the middle here and extend up and down as you choose. Okay, so I will stop there.
So let's see if there are some questions. I have mine, but let's wait for if someone else has some question. So you have mentioned that that there is some relation between your main theorem and the Schutzenberger Evolution.
Mm-hmm. Okay, so I can, yeah, so the relationship with the Schutzenberger Evolution is for this theorem here. Mm-hmm. Yeah, so basically so the way you can think of the Schutzenberger Evolution is so one of my tableaux is giving me all multi-pass last passage values from this corner up to all of these corners. So this spits out a semi-standard Young tableau. Mm-hmm. Okay, and then if you apply the Schutzenberger Evolution, maybe I'll call this T. We apply the Schutzenberger Evolution, we get some S of T. Then you can think, okay, what does that mean on the last passage side over here? So what that corresponds to is, instead of looking at this corner and going to all the last passage values on the top here, what you do is you fix this corner and you look at all last passage values on the bottom there, going back and forth. So that's what the Schutzenberger Evolution is doing at the last passage level. So when you apply the Schutzenberger, so applying the Schutzenberger Evolution tells you that, okay, we knew all last passage values to the top. That means we can apply the Schutzenberger Evolution, which just uses information about that tableau. And then we know all last passage values to this top corner from anywhere on the bottom. Mm-hmm. But what you could also do is you could stop your tableau partway. So you could just sort of truncate here. Okay, so we're building up this semi-standard Young tableau bit by bit. So if we stop at this point, we have a semi-standard Young tableau here. We could apply the Schutzenberger Evolution to this guy and get all last passage values from that end in this square up top here. So in particular, if you apply the Schutzenberger Evolution to all truncated tableau, what you get is all last passage values from any point on the bottom to any square here, where the way you did that is you truncated at this point and you applied the Schutzenberger Evolution and you read off that last passage value. So that's one way of proving this this theorem that I mentioned. I don't know if this has been written down somewhere in the combinatorics literature that you can do this.
Very nice.
Are there any other questions?
So sorry, I'm not aware of this involution argument. So what does it say?
The Schutzenberger involution is just the Schutzenberger involution is a, like, if you have, I'll do this with standard Young tableau. I think I'm getting this correct. So if you sort of have a standard Young tableau like this, 1, 2, 3, 4, say 5, 6, you can apply this Schutzenberger involution and you get another Young tableau on the other side. So it's some bijection between Young tableau and it's an involution because, okay, S squared gives you back the original Young tableau. And the way the Schutzenberger involution is described is in terms of an evacuation procedure. But the reason it was first studied was because of this relationship with RSK. I'm not sure if this particular property of the Schutzenberger involution is the thing that was first shown about it, but I think this is why it was studied in the context of RSK originally. It's because it does this.
Thanks.
Hi, Duncan. This is Nikos Zigudas. So it was a nice talk. So I have a question about this. Is it the Schutzenberger involution something you used for the directed landscape?
No. So the property that okay. So this theorem, where was it? This theorem here, which we realized, or which I should say, János and Balint had for the directed landscape, the function f is constructed explicitly without any reference to the Schutzenberger involution. And I wasn't really aware that you could, I mean, you can kind of get f in an abstract, you can kind of get f in a non-useful way with the Schutzenberger involution, because keeping track of what exactly this function f is not easy with the Schutzenberger involution as far as I know. But yeah, maybe for those, if there's interest, I'm happy to explain what exactly this function f is and how you can prove that this f works.
Okay, yeah, I would be interested. I don't know if it is.
It probably would
there
take
are time limits, but yeah.
I think it's maybe 5 minutes, depending on. Well, okay. I mean, basically, what's happening is you have, say, an n by m matrix like this. And I'm going to pass to, maybe I'll stick with this in the n by n case. And when I get one tableau, I can sort of record this one tableau as a bunch of entries in a triangular shape like this. And so what I put in here is, I put in this box my last passage value for the is it, yeah, for 1 by 1n, and the way that you can set this up is you can guarantee that what's the right way to say this? The way that you can set this up is you guarantee that the sum of all of these squares here up to this point, so the sum of these first 3 squares, the sum equals the last passage value from 1 up to 3n, say, okay? And then that's how you get the first row. And then the second row is sort of obtained recursively, so that in general what you have is the sum of, say, all of these boxes. This is the 2-path last passage value from 1, 1 to, well, in this case, it's going to be 3n, something like that. So this is basically just a way of describing RSK. But a nice way of thinking about this, and so what I claim is that if I identify all of these points here, so I have 1, 2, 3, and so on, you can think of this as shifting the bottom of your matrix up, and I'm going to keep the top of my matrix in the same place. Okay. And I'll let Lij, this is the last passage value, maybe this is taking a bit too long, but this is the last passage value from I'm getting my coordinates confused. Yes, from I1 to Jm. And with these shifted coordinates, I could also define L tilde ij. And the claim is going to be that Lij equals L tilde ij. And this should be true for both last passage values and polymers. And basically the way that you've set this up is we don't know that the Lij's are equal to the L tilde ij's, but we do know that certain multipath.
Can you show in the diagram what is the last passage from which to which Lij?
Yeah, so this Lij should be, this should be, maybe this would be L34.
Oh, okay.
And this is going to be L34 over here. This is going to be L tilde 34. Okay, so we do know certain multipath partition functions slash last passage values are the same. So if you go over here, just by the way that we constructed this side of the picture, we know that if we fix any collection of points here and fix any collection of points here, like this. So if we start in the corner and extend to some number and go that way, then that's the same as doing the corresponding thing over here. Maybe let me. I'm going to redraw the picture just because I think it's getting a bit messy. Let me. So if I have, say, 2 points over here up to 2 points over here, this is equal to these 2 points over here to these 2 points over here, just because that's there's only, just because that's exactly how we defined the entries in this diagram over there. Okay, and again, this is the same for last passage values and for partition functions. So at this point, it's going to be easier to think about this in terms of partition functions. So why is L equal to L tilde for partition functions? Well, say this value here, this is going from 1, 2, say, to, maybe I'll call this k plus 1. So the two-path value from 1, 2 to k plus 1, that's the two-path partition function value, is a determinant of a minor of L, where we pick out, say, the first, so you're now thinking of L as this matrix, this Lij, where we pick out, say, the first 2 rows and the kth and k plus first columns. And so what we know is that certain determinants in L and L tilde are equal. So we have 2 matrices, L and L tilde. So this is L, this is my L tilde. They have entries which are 0 below the diagonal. These are both n by n. And we know that a bunch of their determinants are equal. So we know that determinant of L1 up to J, K up to K plus J minus 1 always equals determinant L tilde 1 up to J, K up to K plus J minus 1. And because they have zeros below the diagonal, you can check that these determinants actually determine the entire matrix. And so then you get that L is equal to L tilde. So in particular, if I set J equal to 1 here, then that tells me that the first row of these matrices are the same. And now I can check that this next entry is the same. Well, I know that the determinant of this top square is the same for L and L tilde. I know this is a 0, and I know what these two X entries are. So I can determine the remaining entry used to compute that determinant. Now I can keep going. I can go this way. I can determine this guy. I can keep going. And now I can go to the third row. I can determine this one because I know all of these. And I know that these two entries are 0. So just like that, you can say, okay, we know we have this upper triangular structure. We know enough determinants that we can determine the entire matrix. So you get that L is equal to L tilde. That's the proof in the partition function context. In the last passage context, you can sort of do this in various ways. One way is to say, okay, look at partition functions, which are the positive temperature version, and take a 0 temperature limit. Another thing you could say is algebraically, the plus times algebra and the max plus algebra are the same as long as we are allowing subtraction in the plus times algebra. So subtraction is what we needed in order to define determinants, but the equality that we showed doesn't involve subtraction at all. So the functions are completely subtraction free. So any equality that's true in the max plus algebra is also going to be true in the plus times algebra and vice versa. So we basically, but we use determinants in the plus times algebra to prove something in the max plus algebra where you don't have an analog of subtraction. Maybe this was a bit jumbled, but hopefully it made some sense.
So this is this looks like some structures in Numi Yamada. Is this what you were alluding to?
Yeah. So this is what when I alluded to earlier that this is the proof, which is the way I came up. I mean, I kind of distilled this from Noumi Yamada's paper. I mean, this is not exactly contained in there, but you know, all the essential ideas are there.
Okay. Thanks.
Yeah, in the directed landscape paper, we had a different approach to this entirely. Sort of not seeing the positive temperature world and therefore not having access to determinants makes it quite a bit more complicated somehow, or a little bit more complicated anyway.
Thanks.
There's a question by Yerlin, which left, but still we're gonna ask the question. Like, is there any application of the shift invariance to understand the quantitative behavior of the model?
I think there probably is, but it's not something like it's not something I've thought hard enough about, but I do think shift invariance should be helpful in, I would maybe not for the thing with these particular models is I don't think shift invariance is as strong as the other, you know, exactly solvable methods which give you stuff about the quantitative behavior of the models. But if you had a model where all you knew was shift invariance and you had access to nothing else, I do think it would give you something. But I haven't worked out, I haven't tried to work that out in detail, again, because these models kind of, there are more powerful methods for proving quantitative behavior.
Okay, so let's see if there are other questions. Actually, another question. I don't want to kidnap you. So, okay, I'm gonna ask that question anyway. So you said that these symmetries allow you to define an RSK on more general polygons. But so this really seems like a combinatorial statement. So do you think it's possible to, do you think this type of generalization holds also for different RSKs? For example, there is the RSK for set value at the tableau.
I'm not sure. I also don't know if the other thing is kind of curious that you get an RSK for these other types of shapes with entirely probabilistic methods, though you could probably go through the entire paper and rework it as entirely combinatorial. I certainly think that's possible. And yeah, I think anytime you have an RSK bijection for anytime you have an RSK bijection on Young diagram-like shapes, you should have an RSK bijection on these more general Moon polyomino shapes as well. I would say so. But again, it's not something I've tried to do.
Okay. Okay, so if that was the last question, okay, maybe we can, I can personally thank the speaker. And yeah, so thanks a lot for your talk. And I think this is the end of the meeting. So thanks a lot everyone for attending, and we will see next week with Eric Bates. So thank you very much, and have a nice day. Bye-bye.